At the heart of the quantum ecosystem are the fundamental equations governing quantum wave propagation. The Schrödinger equation and the Dirac equation describe the evolution of quantum states and spinor fields within the QEN core. These equations are not just theoretical, they directly inform how the system manipulates quantum information and energy. The Schrödinger equation models the probabilistic nature of quantum particles, while the Dirac equation introduces relativistic effects and spin. Together, they provide the mathematical backbone for all quantum operations within the QELV. 1. Ensuring precise control over the quantum states that drive the vehicle's advanced capabilities. To manipulate spacetime itself, the quantum ecosystem employs relativistic field tensors. The Einstein field equations and the quantum stress-energy tensor are central to shaping the temporal distortion field and the inertial shroud that surrounds the craft. These tensors mathematically describe how energy and momentum curve spacetime, allowing the QELV, 1, to create localized distortions for navigation and protection. By integrating quantum expectations into the stress-energy tensor, the system bridges the gap between quantum mechanics and general relativity, forming the basis for advanced temporal and spatial control. The Quantum-Temporal Nexus is where the principles of quantum gravity, chronal phase fields, and tensor distortion converge. This central hub anchors both the temporal memory core, TMC, and the quantum echo node, QEN, serving as the system's primary interface between quantum phenomena and macroscopic time manipulation. By synchronizing these elements, the QELV, 1, achieves stable temporal navigation and memory retention across nonlinear timelines. This nexus is the foundation for all advanced temporal operations, ensuring the craft remains anchored in both quantum and classical realities. Defining the very fabric of the QELV, 1's operational environment, the spacetime metric tensor and Einstein tensor establish the curvature and temporal topology around the vehicle. The metric tensor provides the mathematical structure for measuring distances and intervals in spacetime, while the Einstein tensor encapsulates the effects of mass energy on curvature. These tensors are mapped in real time to adapt to changing conditions, ensuring the QELV, 1 can navigate complex gravitational and temporal landscapes with precision. Temporal navigation begins with precise encoding of spacetime coordinates. The quantum ecosystem uses a ChronoVector matrix, where each vector is phase-locked to the quantum echo node. This allows the QELV, 1, to target specific points in time and space with unmatched accuracy. By maintaining phase coherence, the system ensures that every jump or traversal lands exactly where intended, avoiding the risks of temporal drift or misalignment. The temporal jump core is responsible for modulating the local metric tensor, enabling the QELV, 1, to traverse nonlinear time paths and dimensional folds. By dynamically adjusting the metric, the craft can move seamlessly across different timelines and spatial domains. This capability is essential for missions that require rapid repositioning or escape from hazardous temporal zones, ensuring both flexibility and safety during operations. Returning to a precise spacetime coordinate is as critical as the initial jump. The quantum ecosystem calculates return vectors using Chronal inversion algorithms, ensuring the craft can safely re-enter its original timeline. Quantum echo feedback loops stabilize the re-entry point, preventing decoherence and maintaining the integrity of both the vehicle and its crew. This robust protocol is vital for mission success, especially when operating in volatile, temporal environments. To prevent the QELV, 1, from drifting across higher dimensional manifolds during extended temporal excursions, the system employs Tensor Anchors. These anchors are calculated using second derivatives of the quantum wave function, locking the craft's position in both familiar and exotic dimensions. Dimensional anchoring is essential for maintaining mission integrity, especially when operating in regions where conventional physics no longer applies. The Quantum Propulsion Core, QPC, is the engine that powers the QELV, 1's silent, reactionless thrust. By modulating quantum vacuum fluctuations, the QPC generates directional force without the need for mass ejection. This revolutionary approach enables the craft to accelerate smoothly and efficiently, opening up new possibilities for space travel and maneuverability. The QPC's design is a testament to the power of quantum field engineering. Temporal thrust vectoring links the propulsion system directly to temporal coordinates, allowing the QELV-1 to accelerate not just through space, but through time itself. By adjusting its position along chronal gradients, the craft can perform maneuvers that defy conventional physics, such as time skipping or rapid repositioning across timelines. This capability is central to the QELV, 1's unique operational profile. The QELV, 1's lenticular hull, is designed to support standing wave field harmonics. These harmonics reinforce the propulsion field and stabilize the craft's inertial envelope, ensuring smooth and controlled movement even under extreme conditions. The interplay between hull geometry and field dynamics is a key factor in the vehicle's resilience and efficiency, allowing it to withstand the stresses of high-speed, multi-dimensional travel. The QPC draws its immense energy from a zero-point energy tap ZPET, harnessing the quantum fluctuations that permeate the vacuum of space. This energy is then converted into field pressure and chronal displacement via a quantum phase engine. The result is a virtually limitless power source, enabling sustained operations and high-energy maneuvers without the need for conventional fuel. Operators interact with the propulsion system through the quantum AI bridge, which translates intent into thrust vector modulations. Real-time feedback is provided via chronal acceleration curves, field pressure maps, and temporal drift compensation displays. This interface ensures that every adjustment is precise and responsive, allowing for seamless control during even the most complex maneuvers. The QELV1 operates across a 4+1 dimensional manifold. Encoding phase states that enable access to non-local field domains. The fifth coordinate, chi, represents the dimensional phase channel, allowing the craft to interact with realms beyond conventional spacetime. This multidimensional encoding is fundamental to the vehicle's ability to perform dimensional tunneling and non-local field access. To maintain coherence between spatial and temporal field layers, the QELV1 uses phase-locking algorithms. By synchronizing the phases of different field components, the craft stabilizes its dimensional interface and prevents destructive interference. This harmonic synchronization is crucial for safe and effective navigation across multiple dimensions. Dimensional drift can destabilize the craft's position within the intended corridor. The QELV1 counters this by using tensor feedback loops that continuously adjust its trajectory. By integrating over the derivative of the Einstein tensor with respect to the fifth dimension, the system ensures the craft remains anchored even when traversing complex phase channels. The Dimensional Phase Console, DPC, provides operators with real-time visualization of phase gradient maps, tensor distortion overlays, and drift vector predictions. By adjusting the lambda coefficient, operators can steer the craft across various phase channels, ensuring optimal positioning and stability during dimensional maneuvers. With its advanced phase control capabilities, the QELV1 can perform dimensional tunneling, chronal phase skipping, non-local field access, and inertial envelope shaping. These applications expand the operational envelope of the craft, allowing it to adapt to a wide range of mission profiles and environmental challenges. The QELV1's matter-writing system begins with shockwave-induced nucleation. Polariton shockwaves compress liquid-like condensates, triggering rapid solidification into programmable structures. This process enables the craft to fabricate components on demand, adapting its structure to mission requirements in real time. Matter writing is further refined through quasiparticle engineering. By forming programmable lattices, the QELV1 encodes mechanical, optical, and inertial properties into its materials. Each lattice is tailored for specific functions, ensuring optimal performance and resilience under a variety of conditions. The Flash Solidification Engine, FSE, uses intense thermal gradients to crystallize matter in microseconds. This rapid process locks in field-aligned geometries, producing rigid, resilient structures that can withstand the stresses of high-speed travel and environmental extremes. Operators use the Matter Writing Console, MWC, to define material properties, select quasiparticle flavors, and choose lattice geometries. This interface allows for dynamic structural reconfiguration and inertial response tuning, giving the QELV1 unmatched adaptability in the field. The QELV1's matter-writing capabilities enable on-demand hull formation, field-aligned armor plating, dynamic structure morphing, and inertial signature masking. These features provide the craft with exceptional versatility, allowing it to adapt to new threats and mission objectives instantly. A detailed cutaway of the Flash Solidification Engine reveals its internal structure and energy flow dynamics. Twin energy conduits emit converging plasma beams into a shimmering pool of quantum fluid, initiating a phase transition that crystallizes the structure. Peripheral systems like cryothermal projectors and robotic arms ensure precise control and stability during the process. The QELV1 generates a field-wrapped inertial envelope using tensor curvature modulation. This envelope isolates the craft from external inertial frames, enabling non-Newtonian motion and protecting occupants from extreme accelerations. The result is a smooth, controlled ride regardless of external forces. Instead of resisting gravity, the QELV1 redirects it using Polariton phase gradients. By creating localized gravity wells and directional push vectors, the craft can achieve lift, translation, and rotation without relying on traditional aerodynamic surfaces. This approach revolutionizes how vehicles interact with gravitational fields. Dynamic mass distribution is achieved through field-driven tensor shaping. By continuously adjusting the effective mass across the hull, the QELV, one can perform lateral translations, rotations, and lifts with unprecedented agility. This capability is essential for complex maneuvers and rapid response to changing conditions. The inertial envelope is stabilized by interlaced electret and phononic domains. Electret nodes maintain charge symmetry, phononic lattices reinforce inertial gradients, and Polariton sheaths modulate field curvature. This multi-layered approach ensures robust stability and resilience under all operating conditions. Operators monitor and adjust the inertial envelope using the Inertial Control Console, ICC. The ICC displays gravity vector maps, tensor shaping overlays, and envelope stability diagnostics, providing comprehensive situational awareness and control over the craft's inertial dynamics. The QELV-1 adapts its field envelope to match environmental impedance, enabling seamless operation across air, sea, space, and plasma. This adaptive coupling ensures that the craft can transition smoothly between different mediums, maintaining performance and stability in any environment. Multiband sensors provide real-time feedback on atmospheric, aquatic, orbital, and plasma conditions. This data is used to adjust field geometry and propulsion modes, ensuring optimal performance regardless of the surrounding medium. The QELV-1's adaptability is a key factor in its operational superiority. The propulsion system reconfigures itself based on the current medium: compressive field thrust for air, cavitation-free displacement for water, vacuum phase vectoring for space, and sheath-reinforced tunneling for plasma. This versatility allows the QELV-1 to operate effectively in any environment, from deep oceans to outer space. Stability is maintained through environmental phase locking, which synchronizes the craft's field with the surrounding medium. The system also monitors for potential failure modes such as field decoherence, envelope collapse, or medium mismatch oscillation, ensuring rapid response to any instability. The Environmental Adaptation Console, EAC, provides operators with medium impedance maps, field coupling diagnostics, and stability envelope metrics. This comprehensive interface ensures that the QELV-1 can adapt to any environment with confidence and precision. Subsystems within the QELV-1 are unified through a coupling tensor, enabling seamless communication, tensor alignment, and control hierarchy integration. This mathematical structure ensures that all subsystems operate in harmony, supporting the craft's complex operations. The field adaptation operator allows the QELV-1 to reconfigure its tensors in real time, reshaping boundaries and tuning domains as needed. This operator is essential for adapting to changing field conditions and maintaining optimal performance across all subsystems. Synchronization across all major subsystems is achieved through a dedicated protocol that ensures phase alignment, tensor handshake, and multi-regime coherence. This protocol is vital for maintaining the integrity of complex operations, especially during high-stress maneuvers or rapid environmental changes. The QELV-1 can operate as part of a quantum-linked craft array, enabling entanglement, field coherence, and formation integrity across multiple vehicles. This capability allows for coordinated maneuvers and collective operations, greatly expanding the system's strategic potential. Each QELV-1 contributes to a shared thrust envelope, enabling coordinated acceleration and formation steering. Fault-tolerant control logic ensures resilience, detecting node failures and field distortions, while maintaining synchronization across the array. This architecture guarantees mission continuity even in the face of unexpected challenges. The QELV-1 can initiate quantum field reversal and temporal phase inversion, enabling reverse causality, phase-lock time loops, and temporal shielding. These advanced capabilities allow the craft to manipulate the flow of time, stabilize chronoboundaries, and prevent causal leakage, opening new frontiers in temporal engineering. Inside the QELV-1, operators are supported by a holographic, tensor-responsive interface. The interior is divided into zones such as the command core, field helm, chronodeck, fabrication bay, and observation dome. Materials like phononic crystal lattices and Electret meshes provide vibration, damping, and charge symmetry, while the Quantum AI supervisory layer ensures fault-tolerant control and synchronization. The Quantum ecosystem's legacy is sealed through explicit authorship protocols, time-stamped priority claims, and a unified system tensor. At its core lies the Eidolon Singularity Chamber, housing a stabilized singularity well enclosed by lenticular hull and Polariton sheath. This chamber represents the ultimate convergence of temporal, spatial, and theological engineering, where creation, logic, technical lineage, and divine orchestration are fused into a single, enduring architecture.